So since actually nanocatalysis is the very burning and the thrust area nowadays, because of the demand of renewable energy or the alternate source of energy. So generally we do photocatalysis, electro or the photoelectrocatalysis. And one more actually very interesting part of this actually nanocatalysis, the organic transformation reaction. Since the millions of the organic conversions are known, which are supported by the inorganic materials. So we transform those inorganic materials in the nano form, and then study the same reaction where actually we are able to reduce the reaction time from several hours to few minutes or the few seconds with the help of the nanocatalysts. And the nanocatalysts were also actually used for the water treatment, environmental remedies. So many actually application oriented part actually based on the nanocatalysis. So here today I am going to actually show some of material which actually I will show how to design and we need to use for some time of the nanocatalysis. So when we start actually nanocatalysis, first I will speak briefly over the nanomaterials. Basically, nanomaterials are very fine materials whose grain size lies in the range of 1 to 100 nanometers. So these actually nanomaterials or the nanostructures are of various shapes, morphology, or the geometry, depending on the actually dimension or the or on the shapes, like the nanorods, nanowires, like nanotubes. You can see over here nanotubes, and then these are the nanowires. Then core shell nanostructures, actually where you have the core of one material and the shell of other material. Then you can see the bipods, tripods, multipods, nanocylinders, nano-ovals, nanoflowers. Means many shapes, many morphologies are there, like the nanocomposites are also there, right? And actually, actually, the typical size of any atom is around 1 to 2 angstrom. Therefore, in 1 nanometer dimension, we can arrange 5 to 10 atoms. So, when we approach to this nanometric dimension, the material shows some unusual application because of some unusual reasons, like the confinement of electrons, high surface area, and the large number of electric or magnetic dipoles are highly disordered at the surface. And because of these unusual reasons, these materials could be useful for making electronic devices in memory devices, catalysis, sensors, and energy. So many actually applications are there. So actually, what happens actually when we reduce the size of the objects from big size to the smaller size, then what happens actually we are increasing new surfaces or the new particles over the surface. Therefore, the surface energy will increase for a constant volume, and the surface energy is proportional to the surface area. So the surface area for a constant volume will increase when we reduce the size of the object from micrometer to the nanometers. Now coming to the core theme of my presentation, which is the actually nanocatalysis. Actually, we generally do nanocatalysis either in the form of photocatalysis, electrocatalysis, photoelectrocatalysis, or actually organic transformation. Why we are actually interested in these kind of the nanocatalysis sections? Because actually sometimes we are interested for the fabrication of the medicinal plants, or sometimes we are actually focused on the industrially viable compounds, which are very costly actually, and sometimes environmental remediation or the renewable energy or water treatment. So actually we do have the different kind of the organic transformation, different kind of the nanocatalysis. So actually when we talk about the nanocatalysis, so first actually we need to discuss about the catalysis. Generally, the catalysis requires the three main components: one, adsorption, then reaction, then desorption. Initially, actually, if your catalyst means if it is in the nano size, then it has a very high surface area. Then it can actually absorb the large number of reactants over its surface. So this phenomena is called as the adsorption. And when actually the reactants are adsorbed, then some actually intermediate formation occurs. So these intermediate formations actually involve the rearrangement of the electrons, and which can actually lead to the chemical reaction. And finally, these actually uh, these molecules are dissolved from the surface, and the product formation occurs. This is called as actually desorption. These are the actually general terminology of the catalysis and general steps which are actually involved here. So this is actually, this slide is dedicated for the organic transformations. Actually, millions of organic conversions are known, and here in my research lab at Jamia, Islamia, New Delhi, we are doing actually a lot of organic transformations based on the carbon-carbon coupling, hydrogenation, electrophilic cyclization, amination, oxidation, and so many actually conversions are there. And for these conversions, we actually design very beautiful structures of the metal oxides, which actually act as the nanocatalyst. Like we design copper oxide or the tungsten oxide or copper or silver doped tungsten oxide, ruthenium oxide, some phases of the cerium oxide or some composites of the cerium oxide. Then we actually apply these uh, structurally important material for nanocatalysis for these kind of the conversions, and we are publishing a good number of papers in this area also. But today actually I am going to speak over the energy issue. So actually why we are what are the process actually which is the backbone of to get the hydrogen. This is the water splitting actually. Water splitting is a chemical approach which actually enables the formation of hydrogen by breaking of water into elemental hydrogen and oxygen. So here actually you actually just break water molecule into elemental hydrogen and the oxygen. This phenomena is called as the water splitting phenomena. So this phenomena actually generally requires, this is not actually so easy. This requires the presence of the catalyst, and the second is the light. Actually, light is required to generate the electrons from the nanocatalyst, and these electrons are used to reduce H plus ions in the aqueous solution. And the best source of the light is the solar light. And in the solar light, actually, if you see the solar light spectrum, then the maximum component is the visible light component. And visible, so we need to design the visible light active materials. So what are the visible light active materials? The materials whose optical band gap should be in the visible region, means 1.8 to 3.2 electron volt, and these materials should actually excite in the visible region, which is actually 700 nanometer to 400 nanometer. So how to design the visible light active materials? So we need to make some chemical modifications. So we generally do these chemical modifications either by making the pore shell nanostructures or by doping of some metals over the metal oxide hostilities or some metal chalcogenide hostilities, or by designing nanocomposites, or by designing heterostructure. So we are doing all kind of work in my research lab, where actually we are designing lot of materials by making some chemical modifications, so that actually we can bring their optical band gap in the visible region. And of course, actually because of their small size, they must have the high surface area, so that actually by collectively we can increase their photocatalytic activity, and we can actually increase the ability of these materials to produce hydrogen significantly. So actually, what are actually, there are actually a number of reasons for the energy crisis across the globe, like the overpopulation. You know, the actually population globally actually is increasing day by day. The maximum countries have very poor infrastructure to store actually energy. Overconsumption is there. Actually, people are not aware to actually to use the energy or the utensils which are actually energy based. The lack of storage, and actually the distribution inequality or the energy waste. So many reasons are there. So actually, and the crude oils, like the fossil fuels, is going to actually finish very soon. Actually, it is predicted like by 2050. Actually, we do have actually very small earth sources which actually produce the crude oil. So we are actually looking for the alternate source of energy. So actually, the leading scientists actually have shown that the major component of the renewable energy may depend on water, because the two-third part of the globe having water, so we can easily generate hydrogen. So hydrogen actually is considered as the clean and the green energy, and when hydrogen is consumed as the fuel, it can actually produce water, electricity, and heat, and it is carbon free, therefore it is environmental friendly and has zero impact over the environment. So generally, to produce hydrogen from water, we generally do the photocatalysis, electrocatalysis, or the photoelectrocatalysis. So these three phenomena are collectively called as the overall water splitting. So overall water splitting actually is considered as the most prominent methodology for water splitting to produce economical hydrogen to resolve the energy crisis. And this is the experimental setup that actually here that I am using here in Jamia Millia Islamia. So here actually we need to have the specialized glass cell actually. so which actually allowed for the exposure of the light. We do have this spatial light source. So this cell assembly. This cell assembly, we need to have the distilled water, then we add the sacrificial agent and the required amount of your nanocatalyst. So these microstructure that for which actually I'm talking about over here. So and then we need to actually evacuate, provide the perfect vacuum or the inert atmosphere, and then we expose this solution with the help of the light source. So initially, when you actually expose this solution by light, then the absorption of light by photocatalyst occur, and actually when light is exposed this solution, then the photogenerated electrons actually are uh, uh, observed in the conduction band, whereas the hole pair remains in the valence band. So we need to inhibit the electron hole pair recombination, and we can study this the inhibition of the electron hole pair recombination by actually studying the photoluminescence and the X-ray photoelectron spectroscopy. So these actually electrons are reduced to H plus into the hydrogen molecules, and the holes are utilized to oxidize water to produce the oxygen. So basically, actually holes are used, the sacrificial agent actually are used to occupy this whole structure. Basically, these holes actually oxidize this sacrificial agent. So we generally use the combination of sodium sulfite as sacrificial agent. And some researchers are used amyl alcohol, some for benzyl alcohol, triethanolamine. So several actually combinations are there for the sacrificial agent, and actually we have also tried many sacrificial agents for our photochemical reactions. Then another methodology is the electrochemical water splitting. So electrochemistry, electrocatalysis is the simplest method which is known for the water splitting. And here we use the direct current for the separation of water into the hydrogen and the oxygen. So generally the hydrogen evaluation reaction occur at cathode, and the oxygen evaluation reaction occur at anode. So generally these are the two half cell reactions. This is the reaction for the complete cell. And what about the photoelectrochemical water splitting? Both phenomena are same actually, electrochemical water splitting or the photoelectrochemical water splitting. But the basic difference is that actually we need to modify the cell assembly, and the second we need to use the light source here in the photoelectrochemical water splitting. The rest phenomena are same for this methodology. So we have all these setups in the research lab to make these reactions viable at the laboratory scale. So we have designed for this reaction very beautiful graphitic carbon nitride nanosheets, and we have published this paper in Asia's Applied Nanomaterials. And we have actually generate hydrogen by photocatalysis and photoelectrocatalysis. So actually, this graphitic carbon nitride actually could be considered as an ideal candidate for photocatalysis due to excellent alignment of its band edge with water redox potential. And we prepared these beautiful nanosheets of the graphitic carbon nitride by annealing of melamine at around 520 degrees centigrade temperature. Then we actually bulk graphitic carbon nitride is obtained, and these bulk graphitic carbon nitride is exfoliated with either with HCl or with sulfuric acid. Then very beautiful nanosheets of graphitic carbon nitride could be prepared. And these are the actually electron microscopic plot. This is the SEM image of bulk graphitic carbon nitride, which shows the buffet-like morphology. And here the nanosheets of the graphitic carbon nitride could be seen over here. And the tilting actually, when we exfoliate the actually bulk graphitic carbon nitride into nanosheets of the graphitic carbon nitride, then the tilting of sheets occur during so this exfoliation mechanism actually could be seen with the help of the field emission electron microscopy, which actually I have shown over here. Then before going to photocatalytic experiments, we do the basic characterization or the primary investigation. So we generally do the BET surface area investigations and the optical band gap study, so that actually we could know what is the nature of the material and which light actually we need to use to expose for the water splitting measurements. So here actually we make two different set of the water splitting measurements. In one set, we need to use the triethanolamine as the sacrificial agent, and in another set, we use the sodium sulfide as the sacrificial agent. So when we actually take the triethanolamine as the sacrificial agent, then the amount of hydrogen which was actually produced, it was tremendous. The value of its was around 470 micromole per hour, and the sodium sulfide gives the hydrogen evaluation, which was around 230 micromole per hour. And this amount actually, the triethanolamine, it was giving the apparent quantum yield of 12%, which was the highest actually, as we do have in the literature. Then we do the detailed photoelectrocatalysis, electrocatalytic activity for the HER reaction. This is the HER plot, means hydrogen evaluation plot. This is the OER plot. This plot is the TEFL plot, and this is the turnover frequency plot. So if you see this LSV plot for HER, then it shows the low onset potential for graphitic carbon nitride, which shows the high photocurrent density for this graphitic carbon nitride nanosheets, and the low value of the thermal flow. Both these experiment actually show that the nanosheets of the graphitic carbon nitride would actually show the significant HER reaction, and we also actually estimate the turnover frequency by using the HER reaction, which is shown over in this plot. Then actually we use these graphitic carbon nitride nanosheets for fabrication of the heterostructure. So first we made the heterostructures of the copper ferrite with graphitic carbon nitride nanosheets, and this paper actually we have published the ACS applied material interface. And actually after preparation of the graphitic carbon nitride nanosheets, then actually we mechanically mix with copper ferrite nanoparticle that we obtain by using hydrothermal method, and at 400 degrees centigrade we obtain the heterostructures of the type 2 heterostructures of the copper ferrite and the graphitic carbon nitride nanosheets. So this slide actually shows the primary investigation or the primary characterization of the copper ferrite graphitic carbon nitride nanosheets. So very beautiful actually X-ray diffraction seen over here, which clearly shows that the formation of the heterostructures, and we have prepared the 10, 20 and 38% loading of the copper ferrite over the graphitic carbon nitride. We have calculated the surface area as well as the optical band gap of all the heterostructures. Then we use these materials for the water splitting, photocatalytic water splitting, by making the two different experiments. In one set of experiments, we have used these sodium sulfide and sodium sulfide as sacrificial agent, and in another set we have the triethanolamine as a sacrificial agent. And in both the experiments, we observed that the 28% loading of the copper ferrite over graphitic carbon nitride nanosheets can generate high hydrogen production. And in fact, triethanolamine gives the more efficient result, and the more loading of copper ferrite over the graphitic carbon nitride nanosheets likely reduce the light absorption, and therefore it decreases the formation of the electron hole pair. We have also confirmed this study with the help of the photoluminescence study. Then if you see the apparent quantum yield, then here you can see the 28% loading of the copper ferrite over graphitic carbon nitride can actually give the apparent quantum yield of this heterostructure is 25%. So we have reported this so much high amount of the apparent quantum yield for the first time in the literature. And this is charge transfer dynamics. Here you can see the electronic impedance spectroscopy for this heterostructure, and here you can see the low circular arc for 28% loading of copper ferrite or graphitic carbon nitride shows the high interfacial charge transfer over the surface of the heterojunction. Then we do the Mott-Schottky studies for the pure graphitic carbon nitride, copper ferrite, as well as for the heterostructure. So the positive nature of this flow, positive slope of graphic carbon nitride shows N-type semiconductivity, and the negative Mott-Schottky plot for copper ferrite shows the P-type semiconductivity, and both positive and negative slope could be observed for the heterostructure, which shows the PN heterojunction formation of the heterostructure. And then when we do the photoluminescence study, then here it shows that on increasing the heterojunction formation, then the PN intensity decreasing, which shows the low recombination rate of the electron hole pair. And we have also suggested the band structure mechanism for this type 2 heterostructure. This is the band structure of the copper ferrite, and here is the band structure of the graphitic carbon nitride. When you mix actually these two moieties, then the Fermi level alignment occur, and during this Fermi level alignment, the electrons of the conduction band of copper ferrite tunnel from here to the conduction band of the graphitic carbon nitride, whereas the electrons from the valence band actually tunnel from here to the valence band of the copper ferrite, where actually they oxidize the triethanolamine, and these electrons are used to actually reduce H plus into the hydrogen gas. Then we do the electrochemical measurements for water splitting reaction. This is the OER and the HER plot. This is Chapel flow, and all these studies shows the low onset potential and the low over potential, which shows the high photocurrent density or the low Chapel flow, which is actually significant for high amount of the hydrogen evaluation or the high significant HER activity by using these heterostructures. And we have also obtained the maximum ferritic efficiency, which was around 95% for 28% loading of copper ferrite over the graphitic carbon nitride nanosheets. Then we have designed the heterostructures of the copper oxide with graphitic carbon nitride. And this is the actually reaction methodology. How do we have prepared the copper oxide with graphitic carbon nitride? But the interesting point is that actually here we have made 10, 20 or 30 or 1, 2, 3 mole% of the copper oxide over the graphitic carbon nitride, and then in detail we have actually analyzed the X-ray diffraction for the formation of these heterostructures, and then we do the theoretical calculation. Actually, there is a lattice mismatch between the copper oxide and graphitic carbon nitride. So first, actually, we actually make the structural similarity of the two material during the heterostructure formation. So we stabilize these heterostructure in the orthorhombic form, so that actually the electron density population actually could increase in the conduction band, which is confirmed by these DFT calculations or DFT plots. Then is the photocatalytic measurement for hydrogen evaluation, and here you can see that the 3.5 gram mole of millimole of actually hydrogen is observed after 5 hours of the exposure, and the apparent quantum yield actually is increased from 10 to 18%. So we are going for the first time actually who are going to report the copper oxide graphitic carbon nitride heterostructures, the increment in the apparent quantum yield in this amount. Then actually we do the actually oxygen evaluation and the HER measurements, and actually we are going to actually show in the literature that actually this heterostructure will be the best replacement for the commercially available till now iridium oxide. So because actually we got very impressive electrocatalytic performance for these copper oxide graphitic carbon nitride heterostructure, we got the lower over potential values, low onset potential values, which is shown over in this graph. Then we have designed actually the ternary heterostructures of molybdenum sulfide, boron nitride, and the TiO2. Actually, the work is difficult. Actually, when you increase the layer to layer to layer, then actually we have been successful for designing these materials. Very recently, this paper is accepted in International Journal of Hydrogen Energy, and with the help of the careful X-ray analysis, we have indexed the formation of the ternary heterostructure, and these are the actually very detailed investigations of the electron microscopic studies. So these electron microscopic studies gives very beautiful pictures of these ternary heterostructures. And here this is the optical band gap plot, which gives the optical band gap tuning of the ternary heterostructures, and this tuning could be seen over the HRTM plot, which is shown over here. This is DFT actually theoretical investigations. So when we do the actually theoretical investigations about the structure as well as about the band gap calculations for the density of states, then actually it shows that their structures were as usual as we actually indexed in X-ray diffraction. And but if you see the density of states, if you see actually the band gap separation for MOS2 and BN, it actually corroborate with the U visible studies, but the optical band gap of the TiO2 actually shows the underestimation due to the DF Coulombic interaction. And it is actually further confirmed by when we actually study the band structure calculation for these materials. Then we have in detail measure the photochemical hydrogen evaluation of all combination. Actually, in fact, we get the hydrogen evaluation measurements for the monophasic CiO2, MOS2, B, and then we make the binary combination, then we make the ternary heterostructure, and we have found that the 2.5% MOS2 BN loading over CiO2 can generate the very high amount of hydrogen, which was 2.6 millimole per gram per hour. And in fact, we are the first who shown this novel study in the literature. We also do the recyclability test, and we obtained that up to 4th cycle there is a very small reduction in the hydrogen. Then actually we do the XPS and the photoluminescence study for for exploring the optical band gap mechanism. So you can see the negative shifting in the XPS peak, which actually shows that the electron density could increase over the conduction band. And if you see the PL study, photoluminescence, then here you can see that PL intensity decreasing, which shows the low recombination of the electron hole pair. So actually by this study we are able to show that the electron density increasing in the conduction band, and the PL shows that this structure is stable. So these electrons are free to reduce H plus into the hydrogen gas. So we got the very effective result for the ternary heterostructure for hydrogen production. So this is the optical band gap trailing of the band gap mechanism for photocatalysis. This is the band structure of TiO2, and this is the band structure of MOS2BN binary heterostructure. This acts as the oxidation photocatalyst, and this TiO2 acts as the reduction photocatalyst. So after combining, it formed the ternary heterostructure, and this was the optical band gap structure of this ternary heterostructure. And this is the electrochemical water splitting, and this is the LSP plot for the hydrogen evaluation, which shows the low onset potential, the Teppel slope. Here you can see the low value of the over potential Teppel slope, which was around 91.1 for 2.5% MOS2 BN loading over TiO2, which shows the significant or the efficient HER reaction. And if you see the chronochromatic plot for HER reaction, then only after 4-hour gap, the HER intensity could increase from 70 to 145, means double. And all these studies actually could be corroborated with the electrochemical active surface area, and the electrochemical active surface area was found to be maximum for the 2.5% MOS2 BN TiO2 ternary heterostructure, and this was the only ternary heterostructure in all the possible combinations which gives the effective results for actually photocatalysis, for electrocatalysis, and for other actually heterostructures, for other heterostructures. So now this is the photoelectrochemical measurements, which is here actually we are showing the LSP and other measurements. And here actually we are able to show that the photoelectrochemical measurements are more effective as compared to the electrochemical measurements. So, and this is the transient photocurrent plot, which shows that the 2.5% MBT shows higher photocurrent density up to the 6 consecutive cycles. And this is the EIS plot. 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 Here you can see the lower semicircular diameter of 2.5 MBT, 2.5 MBT invert the accelerated interfacial charge transfer. And here you can see that in the last plot, which is based on the Mott-Schottky plot, which actually shows that the flat band potential of all the compositions for the proper band alignment. And here we are able to show that the 2.5% molybdenum sulfide, boron nitride loading over TiO2 could show see the proper band alignment, as we have shown in the band structure mechanism too. Now coming to conclude my lecture, we are able to obtain very high amount of the apparent quantum, which was 12%, and high Faradic efficiency, which was close to 99% for graphitic carbon nitride, which shows the prominent metal-free semiconductor for producing hydrogen gas through water splitting. And then 28% loading of copper ferrite over graphitic carbon nitride heterostructures can produce high amount of the hydrogen, which was 971 micromole per hour. with a high amount of apparent quantum yield of 25% with high periodic efficiency. And we are going to add the first report of the binary heterostructures of the copper oxide over graphitic carbon nitride, which is able to produce the high amount of hydrogen. And these results actually, in fact, if you see the electrochemical measurements, we have shown the very impressive electrochemical performance of these binary heterostructures. And we have been able to prepare these ternary heterostructures, and we have shown these ternary heterostructures of MS2, B, and TiO2 would actually very effective for photocatalytic hydrogen production, as well as the electrocatalytic and the electrocatalytic HER reactions. So I would like to actually thank and acknowledge for this kind of work to my collaborators, Professor Chari, Professor Banerjee, Professor Mao, Professor Ahmad, Professor Kapra, and Professor Ingole. And I must thank my research group. These are my past PhD scholars. My present PhD group is there, and my funding agencies, GST, SERB, CSIR, Spark, and my university, Jamia Millia Islamia. Actually, my university gave me the freedom and the environment of working environment where actually I'm exploring such kind of work. And Professor Sweta, actually, the biodata you have read, that was quite old. My citation is around 5600, and I have published till now 151 paper, 156 papers, and this is my 127th invited talk, keynote talk. So that was actually quite old. So with these words, I must thank the my chairperson, Professor Sweta, all the listeners, and the organizing committee for inviting me for this wonderful platform. So thank you all for your hosting me. Thank you. So I must welcome if anyone have questions to ask